Okay, coming back to 5G novelty. So what is missing now is the last tier of our 5G atom. And what you see here is new technologies that you can now implement on the software layer. So the softwareization opens up the box that any innovation that we at the university are doing, we can just plug into the network, right? And by all means, this list is not complete. Things that we are doing is, for example, blockchaining, machine learning, network coding, and compressed sensing. Blockchaining is very good for distributed security deals, but it will also eat up a lot of energy. So I will talk a little bit about the last three bullets over here, what you can do. Now imagine that you take these things and you just plug them into the network just by testing it. It's very brilliant. And we have done it, and you will get some examples for that. First is network coding. I will not talk about this, and we have a whole course about this. There's a YouTube channel for that. If you want to know how this works, just look it up. Maybe you have already listened into the course. Otherwise, you can learn about this. In a nutshell, network coding allows you to have resilience and latency in one code. That's a good thing. And it's a code that even works fully distributed in a network without a lot of signaling. So that is the benefit of it, and I will just show you what we have done with that. We have it implemented in a, for example, virtualized environment where you have one host going over 3 switches. The first switch will get the information, and as we know, the next 2 hops are error prone. What we will do is we will code the information here. Then we will pass it on, and one stream, the green stream here, is recoded, and the red stream is just forwarded, like the internet would do it, store and forward. With the green stream, we need here some computing in order to do the recoding. A recoding is something like polishing up the packets to send them forward. And then in the end, these packets are decoded and given to the host too, right? And the controller here will decide which one of the technologies we would like to use. This shows, first of all, that you can bring in network coding as an encoder, decoder, as well as recoder very easily with a controller. You just place them in a certain way. And it will also be able for you with a ComNets emulator to do exactly the same. So network coding and SDN NFV will be one of their projects. Now, if you look at the theory, and this is from ComNets 1, I just brought you this. If you have an encoder and a decoder and some intermediate nodes, if you would create enough redundancy in the encoder to send it to the destination, and you know that some of them are lost, you hope that you will receive enough information on the other side to be able to decode. You can then calculate the number of packets and the delay that such a store and forward scheme will have in an end-to-end fashion. If you make a hop-by-hop coding scheme, that you can use any coding for that, for example, Reed-Solomon, you will just send from the encoder to the first relay, and the relay will fully decode it and then encode it again for the new given error probabilities, and then you will see that now the number of packets will be reduced and the delay can also be calculated here. That is something, as I said, ComNets 1 material. With the network coding scheme, it's like this, that you just send out packets. All the relays are not relays anymore, they're recoders. They're sending out the packets until you have enough packets on the other side. And there's also some analytical things here to calculate the latency and the number of packets. It's a little bit a problem here with these examples, because if the first packet is really corrupted, you cannot recode something later on. But I think you get what I mean by that. So if you then take this and you just do the measurement with that, here you see the latency end to end. The next one is hop to hop, and then you have the network coding functions over here. You have to be careful, because for the end to end, the latency goes up to the hundreds. So here the latency is very high and always higher than the others. If you then compare hop by hop and RNC, you see that RNC is way better than the hop by hop scheme, right? So they have the same amount of packets, but here you have 6 seconds for 50% losses, while here you have something like nearly 10, right? Good. But the gain is even bigger if you have smaller losses in the beginning, right? Then you see that here you're up in 6 seconds, and down here you are under 1 second in the latency. It has to do with the number of hops. Of course, the more hops you have, the more dirtiness you will get into the channel. Here you see it's quite flat, right? It's quite interesting. Good. The other thing that is new is compressed sensing, and there's something with it that I would like to explain more in detail because it has also to do with something with network coding. And the idea is if you, for example, have some storage and you just want to have the source where it's stored, you have to make a source decoding, and then you encode it for transport. On the other side, you decode it after transport, and you would then source encode it for storage again, right? If you would like to move around your storage to a distributed cluster, what you see here is that first of all, you have to gather all the pieces. Then you do the steps that you have seen in between, and then you have data distribution down here. And for us, it would be interesting, is it possible to find a way that we just take packets from a storage and use this as already, it's source encoded, but it's already encoded for transport. So any distributed device could send it out to the other side. And here we have different codes for storage, different codes for transport. Here we are looking for one code. And this means less complexity, less traffic, low latency, more resilience. To motivate our PhD students, we always tell them they are like these heroes from Lord of the Rings, right? And we are going for the golden ring. And only that this time it's not one ring to rule them all. We need one code to rule them all. How could this work? Compressed sensing is one way of a source encoder, right? And network coding is doing something in the network. But if you compare these two technologies, network coding takes linear superposition as compressed sensing is doing it. Network coding is using random coding coefficients, while compressed sensing is using a random sampling. Now, network coding is source agnostic, while compressed sensing is really looking into the source. And in order to solve that, in network coding, you need an overdetermined full-rank matrix and the linear system of equations. And when you have enough of these equations, you can solve it. Compressed sensing can already work with underdetermined matrices. It's just an optimization problem. So it was quite striking to us that they have similar concepts, only that here you look into the source and here you don't care about the source. Important is that this only works if your source has a given sparsity. So I will show you what this means in a minute. So network coding is made for transporting low latency traffic through a mesh network. That's what the thing is. Compressed sensing deals with the fact if I have massive amount of sensors, how can I reduce this amount of information coming in over different sensors? So, and as an example, let's take the following example. You have 8 cameras here, the sources. And after each camera, you have a wireless device, and the wireless device is just broadcasting whatever is there. Then you have a second tier of relays that will receive what they get. So the first relay here will receive from 3 different relays, and then you will move it on until you reach the sink, right? So the question is, what happens if they see different things, right? Then, of course, you will send the data, but data is replicated, right? They will hear all the different streams, and you will see that, oh, there's a lot of traffic coming. If all of this is 1 megabit, you will become something like over 50 megabit to the sink. That's not really good. But what would happen if they would see exactly the same picture? Now, you could agree and say only the first guy is sending the data to the sinks and the other stays silent. That's easy if you know what the first camera has seen and you have a way to exchange this information, right? But this is not what we would like to do. What if we see more or less the same picture, right? Here you have these arc of cameras of Lumia phones from Nokia. They see more or less the same. Or if you're on the highway and you have cars with cameras and there's one car behind the other, they more or less see all the same background. They only have a different car in front of them. So if the information is more or less the same, so there is sparsity in the picture, is there a way to compress the information here at the source Or even better, is there a way to compress even the data on the way forward? We could use network coding to make it efficient, but maybe if you used a combined network coding compressed sensing here, so one code for them, that could even reduce the stream actively on the network. And then we came back to something that we implemented 2009 already, was on the Nokia Symbian phone, where we implemented network coding, and the theory would say if you send out linear combination, as long as not all linear equations are there, you could not decode the picture. But what we saw here for the LENA picture, when you have all the linear equation, you get a nice picture, but even some packets beforehand, you could understand, oh, this is LENA. We never really understand why this happened, because the picture itself was not sparse, but what's sparse was the code that we used. It was a binary field, so we only had 1 and zeros, so the sparsity was in the code. Let me show this in live. So here you receive coded packets. They look like white noise. Here we try to decode this online, and here you see the decoding matrix. White means ones and the black are the zeros, and if you have enough, it's LENA. But you saw already before that there was already something. Now if you combine a clever way of the source coding with network coding, and here we did not use full compressed sensing, we only use some pre-compressed sensing. Look at this, what happens now. Here you get in the received coded packets, but LENA is gradually getting better and better and better, and way earlier than you have seen it before. And that's quite interesting for low latency application, because you don't need the full-blown picture, for example, for the car, whether you have to decide to go left and right, you don't need a 4K picture of that. It's not so easy to make object detection on blurry pictures, we know that, but why not? So here's a way how we now combine network coding and compressed sensing, finding this one code, right? Now, what you have is a bunch of sensors that select one of their peers to be the cluster head. The cluster head has then the task to collect all the data from the given corporation cluster and broadcast it to the next cluster head until it reaches to the sink. If you do this, we assume that you will get 100% of the traffic. If you now switch on network coding, you will, only network coding, then you will see you reduce the traffic by 25%. And why is that? The nodes still give the same information to the cluster head, but once the cluster head is broadcasting something to the next cluster heads, and this cluster head is also forwarding this, you will see that you would create duplicates beforehand. And as this two duplicates, if you recode it with network coding here, would not increase the rank of the matrix, the traffic that will go in here is then reduced. If you then, instead of network coding, would just use compressed sensing, you will see that the streams towards the cluster head are now reduced significantly. Then you will see the data rate is reduced to 30%. Now you see that this is now not a line as before, it depends on the sparsity. So how close are these signals, if it's, for example, audio, how close are these microphones to each other, and what do they hear? And this is the sparsity. The more sparsity you will have, the better will be the compression rates for that. But here you have the problem that you have still the problem that you will create duplicates from the cluster heads. If you want to get rid of them, why not combining both of them, right? So now we combine network coding together with the compressed sensing, and we go down to 25%. In this case, network coding as well as compressed sensing, they did their job agnostically, right? But if you would like to open the box and say, why don't we do the compressed sensing not only at the nodes, but only later in the intermediate nodes, then you will get even better results. They look like this. You go down to 10% in the traffic. The reasons for that is that now we have a combined way, and we do some active compression even in the phase where we would normally do only the recoding. And in order to do that, we had to do a trick, because mathematically both are using linear combination. They operate on fields, but the compressed sensing is using on a real field, and the network coding was working on the finite field. in order to combine them, we had to make a version where network coding was also operating in the real field. And this is how you get the results out of that. And a third thing is AI, machine learning. I just brought you two examples what we're doing here. You can use AI, for example, in the mobile edge cloud to do the traffic management at intersections. Here you see the average velocity on the demand over intersections. Green means the normal streetlights that you have today. Blue means it's AI based, it learns all the time, and the orange one is a communicative AI scheme. So you have communication and AI. And you see this is way better. It has no so much impact if there's a lot of traffic, then also the streetlights will do the job, but especially in the nights when you come, and you often have this situation, you come to the streetlights, nobody is there. And if you communicate with the streetlights, you can do a lot here to gain the average velocity in these situations. AI has not so much an impact here because it's a single intersection. It changes when you have a way bigger city. So here you see way more intersections, and also here communication will help to tell the neighbor intersection, hey, you could expect very soon some more cars coming to you, right? And this is AI for use case, but we also use AI, for example, for optimizing our SDN NFV networks. So manually you can do this, for example, network slicing. How can you manage the slides? No human can do that. So we use AI technologies even for that. The good news, whether it's network coding, compressed sensing, or AI, now what you can do is you can just deploy it in your network as you wish, and this also on the fly. So if we want to map this back to the book, I already told you the book will be of big help. The first part was what I told you today. Here you see the concept, enabling technologies, innovation track. This will take a while to read all of that, but then after building the test bed, I will not bother you with that. You have here different examples. So realizing network slicing, realizing mobile edge cloud, machine learning for routing, machine learning for flow compression, machine learning for congestion control, machine learning for object detection, network coding for transport and storage, in-network compressed sensing, and security for mobile edge cloud. These examples are all examples that you will see in the lecture and in the exercises. And you see that all of that is really part of our 5G atom, right? So you see here the color space where we explain all of them, but also here where they have a dedicated part just for concept, technologies, and innovation. So I hope you find this interesting, and I will now conclude with something about the communication networks.